What's going on, Algebros? In this video we're going to talk about an algebraic procedure which allows you to test equations for symmetry. So recall there are three types of symmetries a graph can have at this point: x-axis, y-axis, or origin. And we saw how we can come up with a relationship between corresponding points by changing either the x, y, or both coordinates to their opposites. With x-axis symmetry, we had to negate or turn the y-coordinate into its opposite. So in an equation, that equates to replacing y with negative y. For y-axis symmetry, in an equation setting, we replace x with negative x, and when testing an equation for origin symmetries, we replace both variables with their opposite. Now, upon replacing these variables by their opposites, we need to simplify as far as possible. And as it says here in the conclusion box, upon making your replacements, simplify. And if the simplified equation is the same as the original, then the type of symmetry that you're testing for holds. Alright, and that's the concept. Let me work out example part A in this video, and I'll create a separate video for part B. We're going to test y squared equals x plus 16 for these symmetries. Let's start with x-axis. So for x-axis, we're going to replace y with negative y. So this variable y gets replaced with its opposite. And since y is being squared, we're going to want to include negative y in a set of parentheses. The right-hand side, there are no replacements, so I'll leave it as is. Now what happens when you square a negative anything is that it turns from a negative to a positive. So if we square negative y, the negative sign will turn into a positive sign, and we end up getting y squared equals x plus 16. Now you'll notice that y squared equals x squared plus 16 matches the original version of the equation, and because of that, we can conclude that should we be able to graph this equation, it would have x-axis symmetry. Well, let's see if it has any others. Let's look at y-axis. With y-axis symmetry, you're replacing x with negative x. So you're going to replace the x on the right-hand side with negative x, and you'll have y squared equals negative x plus 16. There's really no simplification to do other than releasing the parentheses. We get y squared equals negative x plus 16. Now, although it looks really close to the original version of the equation, it's off by a negative sign, namely the x is negative instead of positive in our version that we get with this test. And if there's any minor thing that's off, in other words, if it doesn't exactly match the original version of the equation, then it does not have this type of symmetry. So we would conclude, based on this, that there's no y-axis symmetry. Now for origin symmetry, we replace both variables with their opposite. So x will be replaced by negative x, and y will be replaced by negative y. So on the left, we'd have negative y quantity squared again. On the right-hand side, we'd have negative x plus 16. And simplifying the negative y squared to get positive y squared and removing parentheses on the right, we see that this does not match the original version of the equation again, because we're off by a negative sign. Alright, so we would make the same conclusion As for y-axis symmetries test, there's no origin symmetry. So this equation would have a graph that is only symmetric with respect to the x-axis. And that's how we do it. All right. So hope to clarify this. If you have any questions with the follow-up video, which is the solution to part B. Of course, if there's anything from this video you have questions on, feel free to let me know. Otherwise, thanks for watching another video, and I will see you in the next one.